With the relativistic formula for momentum under our belt, we can now use that to work out the relativistic form of the kinetic energy, right? So that's a straightforward thing for us to do. Let me just quickly show you what we're going to find before we get there. We're going to find that rather than just having, say, 1/2 mv squared, the Newtonian expression, we'll have a somewhat more complicated form for the kinetic energy, but it is straightforward for us to work out where that comes from. Okay, so what do we do? Well, when you talk about kinetic energy, you can talk about building it up from a force that's acting on an object. So if you want the change in the kinetic energy that a particle experiences, we know how to do that. You just look at the amount of work that is done on it. And for the work done, that of course is equal to a force acting on it that's exerted through some distance. Let's say that's delta x. And using the fact that F is dp dt, we can write this as dp dt times delta x. And we can play a little game where we take the delta x and the dt, or the delta t, put those guys together into a velocity, and write this as dp dotted with or times the speed v. Now, that's a nice way of writing things, because we can write down p also in terms of v. It's just m naught times v times gamma, which is 1 over the square root of 1 minus v squared over c squared. And then putting those together, we can write down, if you don't mind me writing this in a more calculus type form, d of the kinetic energy is equal to d of m naught v over square root of 1 minus v squared over c squared multiplied by v. And now we just integrate this expression up to get our answer. And let me just write it down formally, and then I will give you the answer. So integral of the d of the kinetic energy is the kinetic energy. And you can calculate that by just doing this integral that we have over here, v d of the stuff inside, m naught v over square root of 1 minus v squared over c squared. Now, I've not really been using much calculus at all in the discussion that we've been having, so I'm not going to assume that you are expert on doing these kinds of integrals. I'm going to give you the answer in a moment, but let me note, if you want to go through all the steps, there's an office hour question in the timeline to the course where you can look at the calculation, and it will guide you through it step by step. But now it really is just reduced to a problem in calculus, and so this is something I'm just going to give you the answer, because we're not really interested in teaching calculus in this particular set of discussions. So if you do that integral, here is what you find. Kinetic energy will be equal to m naught c squared multiplied by 1 over the square root of 1 minus v squared over c squared minus 1. And that is our relativistic form for the kinetic energy of a particle whose rest mass is m naught and is traveling along with a velocity v, just as advertised. Now, one quick thing that's useful to point out here, which is probably clear from the discussion before, that the mass of an object soars to infinity as its speed approaches the speed of light. Here you see, too, as v approaches c, this expression over here gets larger and larger, so the kinetic energy gets larger and larger, which is another way of concluding, again, that there's no way to reach the speed of light. You can get close, but it would take infinite energy to get there. So let's take a look at a little demo over here where we can just see that spelled out for us. So in this demo, what we are choosing is the rest mass of some object, a particle. Then you get to choose its velocity. And in this column over here, there's a comparison between the result in special relativity and the result that Newton would have given us. And you see that there is a difference between them. And as the velocity of the object gets larger and larger, that difference becomes ever more pronounced. But you do see that when the velocity is small, Newton and special relativity actually do coincide with one another. And that is something that we can derive just by looking at this equation over here, just for one more second. So if I imagine that v is very small compared to c, then I can expand that 1 over the square root in a Taylor expansion. So this then becomes close to, only for v much less than c, I will get my m naught c squared in front, 1 over the square root of 1 minus v squared over c squared. Taylor expand that, and you get 1/2 with a plus sign. So you get 1 plus 1/2 of the quantity inside the bracket, which is v squared over c squared. So again, if you're not familiar with Taylor expansion, that's something that you should learn about. But this is a close approximation to that formula. And then I still have the minus 1 from over here. And that then, of course, is now equal to m naught c squared times 1/2 v squared over c squared, as I start to write ever more downhill. But let me then cancel out those c squareds and write this as 1/2 m naught v squared. That's great, right? So there you see the usual expression that Newton taught us about, 1/2 m naught v squared, 1/2 mv squared. And that's why we have this nice confluence of the Newtonian curve and the relativistic curve at low velocity. But we see that at high velocities, there's a sharp distinction between the two of them. Kinetic energy and special relativity is fundamentally different from what Newton would have thought, and that difference becomes ever more pronounced at larger and larger velocities.